Welcome to The Explainer. Today, we're pulling back the curtain on how the pros make sure our software works. We're going to dive into two really clever techniques they use, equivalence partitioning and boundary value analysis, to test smarter, not harder. Okay, so let's start with a problem. Imagine you're testing something as simple as a font size box. You can type in 8, 12, maybe 72, but what about 1,000 or 10,000? What about a negative number? Or what if you just type in a word, like blue? The number of potential inputs is, well, practically infinite. So how on earth do you even start to test that? Well, here's the big secret. You don't. You absolutely do not have to test every single thing. There's a much more elegant solution. It all starts when you stop looking at inputs one by one and start seeing them as members of a team.
And this idea, this whole concept of intelligent grouping, brings us to our first core technique, which is known as equivalence partitioning. Now, I know that definition sounds pretty academic, right? But the idea behind it is incredibly simple. Equivalence partitioning just means we divide all the things we could possibly type in into a few smart groups, or partitions. And the whole idea rests on this. The software is going to treat every single input inside one of those groups the exact same way.
So if the program treats an input of, say, 10 the same way it treats 50, then they belong in the same group. It's kind of like doing laundry. You don't have to test bleach on every single one of your white t-shirts, do you? No, you test it on one, and you can be pretty confident about what's going to happen to the rest of the pile. So this is how we bring order to the chaos. We take that gigantic, nearly infinite universe of possible inputs, and we slice it up into a few logical, totally manageable partitions. For example, we can make one group for valid numbers that we expect, maybe another one for a different set of valid numbers, and, this is a really important one, a partition for all the invalid stuff, like negative numbers or just plain text.
And here is the huge payoff. Once we have these partitions defined, we don't need to run a million tests. We just pick one single representative value from each group. Test one valid number, test one invalid one. All of a sudden, this impossible, overwhelming task becomes completely doable.
So grouping our inputs is a massive step forward, for sure. But it does raise a new question. Now that we have these groups, which specific values inside those groups are the most likely to break something? Just think about it for a sec. If a program works fine for the number 50, it's probably going to work for 51 and 52. But what happens right at the point where the rules suddenly change? Exactly. Bugs just love to hide out at the boundaries. These are the edge cases, the exact point where a program has to switch from one kind of behavior to another, like going from a valid input to an invalid one. And testing these tricky edges requires a much more specialized tool.
And that brings us to our second technique, boundary value analysis, or BVA. Honestly, you should think of BVA as the perfect partner to equivalence partitioning. Once EP has done the broad work of creating the groups, BVA comes in and tells us exactly where to look for trouble, right on the edges of those groups.
So here's how they work together as a team. Equivalence partitioning is all about covering the basics. We pick one value from somewhere in the middle of a group just to make sure the general function works as expected. But boundary value analysis is all about precision. It's like a laser, targeting the values right at the edge to catch those really sneaky less than or greater than bugs. Let's make this super concrete. Say you have a field that only accepts numbers from 1 to 100. BVA gives us a crystal clear test plan. We test the absolute minimum, which is 1. Then we test its neighbors, 0 on the low side and 2 on the high side. Then we jump to the other end. We test the maximum, 100, and its neighbors, 99 and 101. These 6 very specific tests are so much more likely to find a bug than just picking a bunch of random numbers.
Okay, that's enough theory for now. Let's see how these two powerhouse techniques work together in a real-world example. So, let's imagine a banking app. It has to calculate interest on a savings account, and the rate changes based on your balance. This kind of tiered system is the perfect place to use our EP and BVA 1-2 punch.
The process is actually pretty simple. Step 1. We use equivalence partitioning to map out our groups. For instance, deposits from $0 up to $100 get 3% interest. That's our first partition. Then, deposits from $100.01 up to $1,000 get 5%. That's our second partition. And then, step 2. We use boundary value analysis to zoom in on the exact dollar amounts where those rates are supposed to change.
And here it is, our final test plan. Look how incredibly efficient this is. For each interest rate tier, we have one EP test, something from the middle, like $55, just to check that the basic math works. Then we have our super targeted VVA tests, like $100 even and $100.01, to make absolutely sure the right switches at the exact right moment. We've covered our bases so well with just a handful of smart tests. So you see, by combining these two techniques, we're building a test strategy that's both highly efficient and incredibly effective. Let's just wrap up with why this matters so much. You know, at the end of the day, this isn't just about saving time for testers. It's about building more reliable, more trustworthy software for all of us. EP is great for catching those general functional bugs, and BVA acts like a sniper, pinpointing those really tricky boundary errors. Best of all, this way of thinking applies everywhere, from one tiny piece of code to the entire system working together.
But, and this is a really important but, there's a vital connection to remember here. The power of boundary value analysis is completely dependent on getting those equivalence partitions right in the first place. If you define your groups wrong, you're going to end up testing the wrong boundaries. It's that simple. They have to work together as a team.
So I'll leave you with a little challenge. The next time you're using any app, booking a flight, changing your password, cropping a photo, try to spot the hidden boundaries. Where do the rules of the system change? Because now you know that's exactly where the most important testing happens. Thanks for tuning in to The Explainer.